we want to talk about eigenvalues and eigenvectors. This is just a brief introduction in terms of an example. So we take this matrix, happens to be a stochastic matrix, happens to be the basic sane-demented matrix that we introduced at the very beginning of the course. So here it is. And what we're going to do is we're going to use this matrix to define a transformation T from R2 to R2. First, we sketch 1, 2, 3, 4 vectors equally spaced, four unit vectors. So here's an arc of the unit circle in the first quadrant, and we have similar picture around the whole circle, but that's easy to calculate. So we transform each of these three white vectors, and we get three vectors here. And by calculating the transformation, we get the coordinates of the vectors, and you can check the arithmetic on that because it was done mentally, and it's probably not completely right. So one way or another, we get 1, 2, 3, 4 vectors, but you notice that this vector here maps to this one. And this vector then has actually, in the mapping, it's been rotated a bit in the counterclockwise direction. This vector here, the 0, 1 vector, has been rotated slightly in the clockwise direction. So somehow the transformation takes these four vectors and kind of moves them toward each other in some way. At least that's the way it looks from the four vectors that we've calculated. We can calculate the angles and stuff, but that isn't all that interesting. We have an intuition that if we are collapsing the vectors this way, there's some vector in the middle somewhere, probably not halfway because this is a totally symmetric matrix, but there's some vector in the middle that maps to a multiple of itself. In other words, some vector in the middle doesn't change direction when you map it. Because again, vectors down here seem to go this way, vectors up here seem to go this way. There's got to be at least one point where the vectors don't change direction. And we'll see what happens to magnitudes. I drew these with ambiguous magnitudes. Okay? So we're going to ask the question, okay? Are there any vectors that map to multiples of themselves? Because, of course, if the vector maps to a multiple of itself, it's not going to change direction. Well, we're going to let x2, x1 be a vector that doesn't change direction. In that case, a times x1, x2 should be a multiple of x1, x2. Because if the vector doesn't change direction, the vector you get has to be a multiple of the vector you started with. Well, then we write that is a multiplied by x1, x2 is a multiple of x1, x2 by some number that we choose to call lambda. And then we just do a little bit of arithmetic up here, a little bit of matrix algebra. So again, we write a times the x1, x2 vector equals lambda times the x1, x2 vector. Okay, well, the x1, x2 vector is equal to the identity matrix times the x1, x2 vector. That should be obvious. If not, write out the identity matrix 1, 0, 0, 1 and multiply it by x1, x2. You'll see you'll get x1, x2. Which means, of course, then, that if we subtract this from both sides, we get this on the left side, and we get the 0 vector on the right side. Then, well, vector multiplication is distributive over the vectors that get multiplied. So a minus lambda I times the x1, x2 vector is the same as a times the x1, x2 vector minus lambda I times the x1, x2 vector. Which means that this matrix, a minus lambda I, has to be non-singular. If it was singular, it would be invertible. Then x1, x2 would be equal to the inverse of this matrix times the 0 vector, and that would be the 0 vector. Okay, well, actually the 0 vector is a multiple of itself, but We're not interested in the zero vector. That's a trivial solution. We're interested in non-zero vectors that do this sort of thing. And the zero vector doesn't have a direction anyway, so it's hard to talk about it being in its same direction. So we exclude the zero vector, which means, again, that this matrix has to be singular. It has to be non-invertible. It has to have a determinant that's not equal to 0, and everything else that goes with that. So it's non-singular, which implies that its determinant is 0. Then, I should put a then, or therefore, it's 0, and isn't really the right word to put there. Matter of fact, that's bothered me enough. Therefore, a minus lambda I is 0. Okay, well, a minus lambda I is what? Well, a minus lambda I is, I never have written that out, have I? But lambda I is lambda, oh, yes, I have written it out. Okay, a minus lambda I is the original matrix minus the vector lambda, or the matrix lambda 0, 0, lambda. Okay, because of course, lambda times the identity matrix gives you this. Write it out if you don't understand. And then when we subtract these two, well, we get 9 minus lambda, 0.2 plus minus 0, 0.1 minus 0, 0.8 minus lambda, gives us this. The fact, or the condition, that the determinant of this matrix is 0, I'm looking for my 0, it's all the way over here, but the determinant of this matrix is 0, well, we write out the determinant of the matrix. Okay, here it is. We simplify it, and it's equal to 0. This is a simple quadratic function. We could solve, or quadratic equation, we could solve for lambda using the quadratic formula if it comes to that, but in this case, this is easily factored into lambda minus 1 times lambda minus 0.7, telling us that solutions are lambda equals 1 and lambda equals 0.7. So we've established that for these two values of lambda, this matrix and this matrix is non-singular. It's singular. The implications of that, well, if lambda is 0.7, then a minus lambda times x1, x2 is 0, 0. Here's your a minus lambda I matrix. And of course, 0.9 minus lambda is 0.9 minus 0.7. If lambda is 0.7, 0.8 minus lambda, 0.8 minus 0.7. You do the arithmetic, and this tells you that this matrix multiplied by x1, x2 equals 0, 0. This is equivalent to two simultaneous equations. We have them here, and we can see, if we look at it just a little bit, that this equation is just double this one, so they're essentially the same equation, they have the same solution. So that x1 equals negative x2 is a solution for both equations, and that's very trivial, you can work that out very easily. Well, if we let x2 equal t, then x1 equals negative t. So any vector of the form x1, x2 equals negative t, t, which of course is t times negative 1, 1, maps onto 0.7 times itself. Remember that lambda is the factor by which you multiply the vector that satisfies these conditions to get the transformed vector. So any vector that's a multiple of negative 1, 1 maps onto a vector that's 70% as long and in the same direction. So that's pretty profound. And you have no idea at this stage of the course just how profound that is. it's a really, really big deal. Especially since we can come over here and do the same thing for lambda equals 1. Well, we substitute 1 in for lambda, and here's our matrix, and here it is. So that matrix times the x1, x2 vector is equal to the 0 vector. And we write out the two equations, and we get two equations that are identical except one is the negative of the other. They have exactly the same solutions. And in both cases, then x1 equals 2x2, as you can easily verify. So for x2 equal t, the solution is 2t. Okay, x1 is 2x2, so if x2 is t, x1 is 2t. And that's equal to t times the vector 2, 1. And it follows then that any multiple of 2, 1, of course this represents any possible multiple of 2, 1, maps 2, 1 to itself. Because lambda equals 1, unlike over here, where it maps the vector to 0.7 times itself, shortens the vector by 30%, this one maintains the length of the vector. Okay, so there we have it. So here are two eigenvectors, negative 1, 1 and 2, 1. Well, let's just picture them and picture what this tells us. So here's the eigenvector negative 1, 1. Here's the eigenvector 2, 1. And the picture would be a little prettier if I labeled these vectors with their corresponding colors. I started doing it in white, and then decided I wanted to color code them. We might as well color code the coordinates. Okay, so here are the two vectors. Now they're not orthogonal. This one is in a region where, if you recall the original picture, things down here turn this way, things up here turn this way. Okay. This one is in a region where everything either turns toward it or away from it. You can map it out. You can take a bunch of vectors around a unit circle and see how they map. Take vectors at 30-degree angles all the way around the circle and see how they transform. See what kind of a picture you get. Okay, well, now we have the transformation. Then takes this vector to itself. It's still 2, 1 down here, but takes this vector to 70% of itself. So that this vector is still 2, 1. It's lambda times itself, which is 2, 1. And this vector is negative 0.7, 0.7. Its eigenvalue, lambda equals 0.7, multiplied by this vector. So this vector down here is negative 0.7, 0.7. Now I had just used the term eigenvalue and eigenvector. These values of lambda are called eigenvalues. And the vectors that we get for those eigenvalues are called the eigenvectors. So we have eigenvectors with eigenvalues 0.7 and 1. Eigenvalue 0.7 on this vector, 1 on this vector. This vector maps to 1 times itself. This vector maps to 0.7 times itself. Furthermore, we've got this dotted blue line. All the vectors that are multiples of this, all the t times 2, 1 vectors, are on this line. And all the vectors that are multiples of this one, t times negative 1, 1, are on this line. So I got a note here, any vector in the blue line maps onto itself. Okay? Just like this one does. Any vector on this line maps onto 70% of itself. So what's happening? Your space in this direction, or your plane if you wish, in this direction doesn't expand or contract. In this direction, everything contracts by 30%. This would cause your unit circle to become an ellipse. That's worth mapping and worth looking at. Okay, now the big deal statement. If B equals a set 2, 1, negative 1, 1, well, that's a basis for R2. Not just a basis, it's a basis of eigenvectors. Okay, and one really cool thing about the basis of eigenvectors is that the matrix that transforms the space relative to that basis, relative to the eigenvector basis, your linear transformation T, which we originally don't have the matrix here, but defined by that A matrix, relative to this basis, the matrix for the transformation would become diagonal. Okay, so relative to the eigenvector basis, the transformation T here is represented by a diagonal matrix, and this is a big, big deal. You will find out a little bit about how big a deal it is. I think your text has probably mentioned, though, that in the introduction, that diagonal matrices are really neat, because if you have a diagonal matrix and want to raise it to the 40th power, all you got to do is take the 40th power of all the numbers in the diagonal. You can't do that with a non-diagonal matrix. There's no simple way to calculate the 40th power of the matrix. Now there are ways you can decompose the matrix to make that a little easier, but there's no totally simple way in the sense of the simplicity. There's no way as simple as just being able to take the powers of all the elements. Okay, so, and that goes on quite a bit. You could also do an orthonormal basis just by dividing this vector by its magnitude, which is the square root of 5, and dividing this one by its magnitude, which is the square root of 2. So if you have an eigenvector basis for a space, and you don't always, the total rotation matrix won't map anything onto its own direction. Okay? But to the extent, or in the subspaces of a space where you have eigenvector bases, you can orthonormalize them. Well, you can't actually orthonormalize them, but you can normalize them. And again, get a much simpler representation of the matrix and a much simpler picture of the entire transformation.